Okay, thanks everybody for coming. I've got 15 minutes to talk and 26 slides, so I'm going to go pretty fast. So don't watch me, watch up there, because I'm not going to be able to say everything that's on slides, right? ISA 106 is using procedural automation. It's about automating procedures. There's been a lot of efforts in industry to automate procedures in the past. And why don't you go ahead to the next slide. There's a number of drivers that create this case for change in our industry. Among those are the large population of operators that are retiring. It depends on what process plant, but a lot of our units require 5 or 7 years for an operator to get board qualified, because they need to spend enough time running the process to create a dynamic mental model. And frankly, we're not replenishing those people as fast as we're losing them. So that's a threat to all of us. Next slide. Additionally, a lot of errors and fatalities and catastrophes have been linked back to failure to follow procedures, as well as some of the gaps that were built in when automation was deployed. And we're hoping to address that with this standard as well. Next slide. So here's a couple of examples of refinery incidents. You don't have to be a highly hazardous industry in order to have incidents. It just means that a highly hazardous one's going to be more flashy, more dangerous. But anytime you have an abnormal event or an unplanned event, and it's not what you wanted to happen, right? This is an opportunity to do that a little bit more robustly. Next slide. So what we're describing here are the different operating modes of using a distillation unit. So you may be in frequency, you may be in total reflux. I think some places call that tail to mouth, or we all use different terms in different companies. But the point there is, whether you're changing your feedstocks or you're changing your operating mode, we're expecting operators to execute procedures to get from one place to another. And my argument is, if you know what the answer is and you know what it has to look like, then we need to try to put the effort in to write that into the code. Next slide. So here we're talking about skills leaving the workforce. A major refining company lost 25,000 years of experience when they had 100 operators all retired about the same time. We hire them in batches, and it turns out then they retire in batches, so that's not terribly surprising. Another major chemical company analyzed their demographics and realized that 75% of their operating staff was going to retire by the end of the decade. So that's a scary thought when you recognize that, and you also know that it takes 5 or 7 years for an operator to really get competent, not necessarily best on the board, but competent at being a board operator. Next slide. So several companies have made efforts at automating procedures. There's been a lot of efforts, usually driven by an individual champion within the company, and oftentimes those were too complex or unwieldy to be maintained, sometimes too expensive to do it that way. So this was another justification for why we all got together to make a committee. Go ahead, next one. Uh-oh, we're hung up.
Doesn't want to advance.
So, all right, where's my paper copy? Sorry about the technical difficulties there, guys.
Just tell them it's not advancing.
For those of you online, the slides are not advancing, so we're working on that, but I'm going to go ahead and continue through the presentation, and we'll refresh the screen when we can. So the ISA 106 committee recently completed the first of 3 technical reports. That's available at isa.org/standards. The second technical report that we're working on is the automated procedure lifecycle. Everybody who's in automation as a career knows about lifecycle management. And the third is going to be basically a appendix, a book of examples on how to apply. After these technical reports are issued and we get feedback from all of you guys, then we'll go about the work of creating a standard. So it starts with these 3 technical reports, gather the feedback on each one, and then move on into a standard. Next slide.
Not going.
Still not? Okay. So the models and terminology is the first technical report. This is the committee's current thinking on how to organize and approach the procedural automation. Part of the reason why some of the previous efforts to automate procedures were, I'll say, frustrated, is you really need to structure your code properly, because if you just try to pile it on an existing architecture, it gets very complex very quickly. So the way that you model the automation solutions needs to have some rationale behind it, right? It can't just be convenience of the programmer. I think you skipped one on me. Okay, I see. So when we're talking about process states, procedural automation is centered on the major pieces of physical equipment. So the conceptualizing the unit operations in the field, right? So if you build a software model or a state machine that conceptually reflects or virtually reflects that model in the field, we found that that's an approach that scales up pretty well and it's maintainable. So that's some of the structure of the code that I was describing a minute ago. And then, of course, all pieces of equipment, all unit operations are going to have a startup function, shutdown, transitions, and the possibility of abnormal situations. So when you structure your object model with a state machine, you take those procedural steps into account. So this is a so-called state-based control, right? So part of what we did is we came up with the physical model. I'm not going to read that to you, but the device, equipment, unit steps are probably the most important for building your architecture. The plant area just naturally falls out after you put those blocks together. And most commonly, we'll build state machines for state-based control at the unit operation level. Sometimes you may have a state machine at an equipment level if you've got, dual pumps or multiple pumps that you want to facilitate operation of, but typically it's at the unit level. Next slide. So this is an example of mapping these concepts to different industries. Next slide. And again, those are examples of mapping the concept. So one of the challenges when we work in these ISA standards committees is the fact that we all use the same words for different things, and we don't always recognize that when we're speaking with each other. I'm saying state and you're thinking mode, and we don't know that we're not on the same definition. That's why all of our standards have 40 pages in the front end of definitions. Next slide. So we're going to jump into an example of an ethylene furnace. Go ahead, next. So the plant area is the group of furnaces. The units is each individual furnace. Next. And then, of course, within the furnace example, you've got all of the components. So what we're gonna do when we build an object model or a state machine model, a unit model, is you collect all of the I/O associated with that unit operation, and all of those are rationalized as well as all of your alarms. So your alarms, because we took into account 18.2, your alarm rationalization happens on the front end, so you don't have nearly as much load on the back end of rationalizing alarms. So alarms are part of your I/O from that point of view, and you collect these and group them. I'm not going to get into too much detail on how you actually do it into subcomponents, and then basically you take the sand and the straw and you make bricks and you build your components out of bricks, build your walls and your buildings out of bricks instead of trying to build your walls and your buildings out of sand. You know, you take the smaller pieces, make bigger pieces, and those are the pieces you work with. Next. So this is really just definition of what those different physical terminologies are: device, equipment, unit, plant, area. So the definition of a procedure, you'd be amazed how much time we spent talking about definition of procedure in the committee meetings. A lot of us, you know, I don't know if anybody here is from Exxon, but you know how Exxon likes to say process instead of process, and we all emphasize things so that we know we're talking about different things, but that's only if you're part of the clique. So we spent a lot of time talking about a procedure because, you know, if you back up, you say, well, a procedure is anything that you do similar in the same way, right? Maybe you have a procedure for going from home to work, right? And we had to all get on the same page about that. So we defined procedure, because if you're going to say procedural automation, you need to define your words. So procedures are associated with objects in the physical model. So you don't necessarily have a plant procedure. And the way that I think of that I find useful is, you know, not necessarily to define the procedure concept by the written document, because there's so much variation on how we all do that, but from the operator's point of view, what is the procedure that the operator's going through? And sometimes, depending on how you manage your paperwork, that's more than one document, right? For them to do the thing they're trying to do is the procedure with reference to the physical object model. Next slide. Okay, so how it's programmed and what language it's programmed in doesn't really matter. How you solve the problem doesn't really matter from the point of view of procedural automation. If you're really, really in love with ladder logic, that's cool. You can do it that way. Some other tools I find more useful, but we're not dictating how it's implemented. So that's up to you and your control system architecture platform. Next. So this is sort of what I described about the procedure and getting into the operator point of view to delineate what's the procedure for that unit operation. Next. So here, a procedure in this case might have more than one implementation module and multiple tasks, right? And where you draw that box when you're segmenting your plant, it's heavily influenced by the operator's point of view, and it's heavily influenced, at least when I do it, it's heavily influenced by the operator's point of view, and it's heavily influenced by the physical model. So one of the things that you look for is patterns in your P&IDs, because you're going to create coding efficiencies, right? So if all of your tanks have a single pump and they have the same valve configuration with a recycle or a minimum flow orifice, then that might be something that you describe as a convenient sized brick or object to use. And then when you're working with operators to gather their knowledge, you talk about how do you interact with this. This is going to be a unit, right? Next. So command, perform, verify is very important, and it's not as important, frankly, whether it's command, perform, verify or command, verify, perform. But the idea here is the operator issues the command, and before you put energy into the system, right, whether that's start the pump or introduce steam or whatever the energy is to the system for that unit operation, you verify that everything is as intended, right? So this means that you make good use of your instrument failure detection, make good use of your limit switches. If your valves are not lined up, if your pump discharge valve is not open, it's probably not a good time to start the pump, right? But the reason I said sometimes you need to switch the perform and verify is sometimes you need to put energy into the system to verify that everything's okay. And that's fine, right? You do that by exception. Next. So again, talking about alarm management, rationalizing alarms on the front end saves so much time and makes such happier operators, right? And you know, you need to, when implementing 106, you need to have a process for collecting that information and then deploying it into the code so that you don't end up with, after the project started up, now I've got this list of chattering alarms that somebody could say, you should have known that going in, but we didn't code for it going in, right? So a plant automation design technique that assigns process states defined and define transition procedures. That's really a restating of what I was talking about. But we use some common approaches that we've found useful. So startup, shutdown transitions, abnormal situations. And this is not new technology. A lot of companies have been deploying this very successfully for a lot of years. And there's data showing the value is there, right? So I'm not trying to sell you on it. I'm just trying to let you know this is not a pipe dream, right? This is not vaporware. Next. So here's a quick state-based control example. I'll let you guys go ahead and read that. One of the things that you did not hear me talk about much is abnormal condition handling. So depending on the complexity as well as the hazard of the process that you're trying to set up, you may want to build in specific abnormal condition handling, and that can be event driven or state driven or both, right? But that's one of the big benefits that we see in taking this approach. Go ahead. So here's an example of control system architecture and what it looks like. See, you guys have seen these sorts of diagrams before. Go ahead. So here's a few key models. We really can't talk too much about models, right? Because the way that you conceptualize a problem has a lot to do with how you approach it and how you solve it. If we're still all in the habit of looking at the control problem, of solving the control problem as identifying valves with transmitters and just making a loop, that won't get you here, right? You got to change the way you approach the problem. Next. Okay, so successful execution and management helps to get us to the point of more safe, more reliable operations more reliably. The ISA 106 committee continues to work on this. We finished one technical report. Not to sound like I'm whining, but it's amazing how much work it is to put these things together. So when somebody asks you to be on one of these committees, please do it, but also recognize it is a commitment. And of course, for more information, you go to isa.org or you can contact Charlie Robinson. It's a great resource. I always stay in touch with Charlie. That's crobinson@isa.org. You guys can contact me. I think we will be able to share this presentation, make it available on the Baton Rouge website. And I think I have 2 minutes for anybody who has a burning question or anybody online with one.
Yeah, we'll cover questions in a minute.
Okay, great. Thanks very much.
Okay, can you hear me? Okay. Okay. So yeah, come on over here. We're gonna what we're gonna do, like I said, we changed the format of the meeting a little bit. So what we're gonna do now is just kind of an informal interview. I'm gonna talk to August for a little bit. If you have questions, we're gonna have a section for that. And what I'd like you to do is, if you're online, submit the question to Brent through chat. If you're here, just kind of walk up and write down a piece of paper for him, something like that. Basically, think of Brent as Roz from Frasier. He's going to be the screener, and he's going to just kind of keep things moving that way. So anyway, August, again, thank you for agreeing to do this presentation. I really appreciate it.
Thanks for having me.
I think it was really informative. Okay, so you talked a lot about the model and the way things are put together. Okay. And I realize that's kind of the first step to get everybody in the world in agreement.
Mm-hmm.
But I kind of felt like the main, you don't have to have the model. where I've seen this done, I've seen this done in a few places. I've seen it done in a DCS for like a major chemical company.
Mm-hmm.
But then like Triconics also uses this for their compressors.
Mm-hmm.
They roll through different steps. And in Triconics, basically where you are is just an integer. So if you're in, there's an integer register. If you're in the startup,
Yep.
it's 1, then it's 2, then it's 3. And so they don't really have all that built. Do you think this model's really that important?
I do. I think they're leaving something on the table by not establishing that cognitive model, to be honest with you. So not every implementation of a sequential function chart is the same thing as what we're describing. The building of that object model and the conceptualizing of it from the operator's point of view pays dividends, right? So there's been a lot of research since about 1988 that I'm aware of on operator cognitive models, And one of the things that we've learned is, even operators in the same, we'll say an ethylene unit, that initially got the same training and went through the same, creation of their cognitive model, will experience different things throughout their years, and they may be, even if they see a very similar event. Ethylene plants are complex, right? So it depends on what you're looking at when that happens, how they're going to learn. And so humans learn by updating cognitive models. That's how you know where your bumper is, even though you can't see it when you're driving your car, right? And we use these models. So I described just now a physical model, but we use all our cognitive models to constantly make predictions, kind of like the way a DMC works, right? And recognizing how the operator functions enables us as automation professionals to set them up for success. So here I'm gonna give you an example of how humans use models to make predictions, and this is a verbal model, right? But all of us right now, or all of you guys are listening to what I'm saying, and your mind is continually predicting the very next word I'm going to say, right? So somebody in the room or online might have been thinking I was going to say utter, right? Because that might work, but that's uncommon, right? So that's just an example of how we work, and recognizing operators are people too. So I think there's a lot of a lot of value, and perhaps not everybody on the committee has the same level of emphasis on that, but I think there's a lot of value in making the model apparent and part of the operator experience, because it works against cognitive model divergence, which is what allows two operators with the same years experience in the same plant see the same thing and take different choices. That's because they're running a different cognitive model.
Okay. That's a lot of words.
That's a lot of words, but it's a complex portion of what we're doing, and it's hard to say that succinctly.
Okay. No, that makes sense. I'm just kidding.
Yeah, no,
So
fine.
So what's so you talked about the advantages, right? Driving force for it. You talked a lot about operators. Talked a little bit about alarms. Is that the driving force? What's gonna make somebody change and make somebody do this?
What's the real case for change?
Yeah.
Well, at a very high level, safe, reliable operations. But so Dow has data which I have seen, but I don't have to share, right? That shows return on investment, where deploying model-based control, state-based control, enables, we'll say, a latex unit to have a positive return year after year. Typically, when you deploy operating unit, the best it ever runs is when it's fairly new, and you have to put a significant amount of capital into it to debottleneck it or something else to get it to pick up again. But it usually demonstrates a return on value decline. There's data that shows automating better changes the direction of that curve, and that's a big deal, right?
Yeah.
Now the economics of that depends entirely on what you're doing.
Yeah. Okay. Y'all have kind of worked out the model, or y'all published the model portion. Is that right? Is that what I understood?
Model and terminology.
Model and terminology is kind of set. The next step. What was the next step?
Life cycle.
Life cycle. What does that mean? Is that life cycle of the standard? Is that what?
Well, so life cycle is really addressing. It's not life cycle of the standard. It's life cycle of the product that you put out after all that automation effort, right? So there's the handoff. You get your project group together, and they spend time harvesting all of this information and embedding that knowledge, codifying it into the automated product, handing that over to automation, handing that over to operations, and then what, right? So then, if operations doesn't, engage in continuous improvement on that, you're not going to see that climbing return on value, return on investment.
Okay. And then after that, then it'll be examples.
Examples.
And those, what do you think those examples are going to look like?
Well, from the time I've spent in the committee meetings, we use a lot of ethylene plant examples because they're non-trivial.
Yeah.
Right. We also use trivial examples, recognizing that some of the concepts we're sharing are new to folks, and they need to see it small before they can see it large.
Yeah.
But we don't have a whole lot of agreed upon examples beyond that. So that's really further down the road than what we have today.
Okay. Okay, and then, granted, this is an opinion question, right?
Mm-hmm.
But look down the future. You finish the examples, you get feedback, you set the standard.
Right.
Is it going to make a difference? Does publishing an ISA standard today affect change?
Yes and no. It really it sort of depends. You know, each facility and each company is going to adopt this or respond to this differently. So when you look at when the SAD4 came out, it was aggressively ignored for a long time by a lot of people.
Right.
Right. And you know what? Automation folks we're skeptical and we're slow to change, and a lot of that is good. There's good reasons for that, right? So this isn't going to come out and change the world the day it comes out, right? I recognize that.
Okay. All right. I mean, my opinion is that by itself, it's not going to change the world, right?
Mm-mm.
But it's more ammunition for people who want to do this already. I think there are a lot of people in a lot of positions who, like in your position, you're a global leader in Castro. So as an integrator comes in and wants to do code,
Right.
it's another thing you can point to of, hey, look at this. I really want this done using these principles, using that. So it's just a little more ammunition.
Yeah, I don't know if I'd call it ammunition. I think I'd say validation, right? Okay. Because if I'm a relatively young engineer or even an experienced engineer and I'm trying to sell these concepts to my boss, and how many of us automation professionals have non-automation bosses, right? So we're trying to tell them about something that they don't necessarily know all the words anyway. Okay. Being able to refer to a global consensus standard does add a lot of validation because, hey, I've been a boss, right? Sometimes when somebody's giving you an idea that's very new to you, you have to go, did I hire a kook? Right. I've never heard of this before, right? And we're all people, right?
Okay. Makes sense. So, all right. So, again, appreciate the topic very much. I just, while we're here, how did you get into automation? Is this like something you wanted to do when you grew up? How'd you fall into this hole?
I've asked the same question to a lot of my mentors when I was younger. How did you get into this? And we all have stories of how we slipped and fell into it and liked it there.
Yeah.
My first role coming out of college was as an instrument engineer, and that was the first step. I was an instrument maintenance engineer, and I was doing small projects in that facility, and enjoyed the challenge of it. In automation, you get to touch on so many things, discipline-wise, right? You need to know, well, not so much anymore, but you used to have to know something about pneumatics. You've got to have a good grasp of mechanics. You need to come up to speed on fluid dynamics. I'm an electrical engineer. A lot of us are in automation or mechanical engineers, chemical engineers, and basically to be good in automation, you've got to be really good in physics, right? Right. And then take it into engineering by applying the physics.
Okay. Cool.
1 minute.
You got to.
Sure. And one more thing that I want to kind of bring up too. Back on the topic, one of the guys who's working with the committee, Yaya from Dow.
Yeah, Yaya's very impressive.
I listened to a talk that he did on it, and one of the things that you emphasized it in the talk, but I don't know if it was as clear. One of the things that I found interesting was that you talked about command, then perform, then verify, right? A lot of times when I first heard about state-based control, I was thinking, okay, the computer's going to tell that I'm in the filling step, right?
Oh yeah, that's a great point.
And then it'll adjust the alarms and all that based on what's going on.
Yes.
But Yaya really was able to stress, no, the operator puts it into a step, and then the control system responds.
Yeah.
And it's really a different philosophy.
It is, and I'm really glad you brought that up because I keep bumping into that a sort of upside down approach, right? Yeah. So a lot of programmers want to approach the problem of I'm going to look at the measurements and based on the measurements in the field, I'm going to determine the state and let the operator know. That approach won't get you here. Right. You're going to spend a lot of time on that and get frustrated. the way to implement these concepts is to recognize that the operator owns and determines the state. Now, depending on the level of automation that you want in your facility, it may be that other states are determining the state of a given unit operation, right? Because it's a downstream thing and it needs to follow, right?
Well, especially the trip to abnormal, something like that.
Right, right. This goes and shut down, so that better go and shut down, right?
Right.
But the point that you're making there, which is great, I'm glad you brought it up, is that the operator owns the state. The operator makes that command of state change. Now, it may be that the system lets him know that everything's verified and it's ready to go to the next state or the transition or whatever. But the operator is still the operator. They're still in control.
Yeah.
They're just not controlling at the element level. And by element, I mean the valve, right? Yeah. So if you've got procedural automation in place and an operator is throwing a valve in manual and messing with it, something's not right.
All right, good. Glad we're on the
Yeah,
page there.
that was a good one. I'm glad you brought that up.
We're gonna kind of start taking some questions. Before we start that, I wanted to, at LSU they always announce the attendance, attendance records. Personally, I think they ought to announce gross profit because that's more important to LSU. But for us, for ISA, we've had a pretty good attendance at this meeting. We have about 15, 20 people here in the room and another 40 to 45 online. So I really appreciate everybody who's connected in. I think this can really kind of help the organization. So, Brent, what you got for us?
Okay, we have two questions. One, is this an extension of expert systems that made a splash in the 1990s?
I'll let you handle that.
I'm not going to say it's an extension of that, but certainly those sorts of efforts, just like other efforts to automate procedures, have influenced what we're doing. So some of the same people that worked on that are contributors, right? So I wouldn't say it's an extension, but I recognize the influences there.
Why do you think those failed?
I think a lot of it had to do with how you structure the problem,
okay,
right? So if I can bring all of us back to college when you were working in calculus or in circuits, if you're an electrical engineer, and one of the first things you do is you redraw it so that it makes sense and it's easier to work with.
Right.
Because sometimes when it's handed to you, it's just a real hairy problem, and you have to. What they used to say in calculus, you have to massage it till you recognize what to do with it, and the way that you parse the whole nebulous problem really determines, structure influences behavior, so it really determines how far you're going to get.
Okay. To me, I got more of a programming answer, right?
Yeah.
When I hear expert system, I imagine another server
Right.
who's then telling the control system what to do. And so you have the vulnerabilities of maintaining that other piece of hardware, that other system, those other people, whereas this structure is more, this is within the control system. And it's by the same people, maintained by the same people.
Well, and that's a good point, right? Because at no point did I necessarily describe that this is code that we're putting in the BPCS, right? This is not a separate system on top of the BPCS. This is the way you program the basic primary control.
Appreciate it. And thanks for the question. Who asked that? Do you know?
I do not know. It was handed to me. There we go. Jeff Young, Syngenta.
All right, Jeff. Appreciate the question, Jeff.
All right, the next question comes from Bruce Moore at Maverick Technologies. August, is it possible to get these ideas implemented with just bottom-up industrial efforts, or must top management push it down?
Bruce is setting me up. I think it is possible, right? But you're going to have to be a pretty charismatic, influential person to get that, right? And there's a challenge. There's always a challenge in any corporation with a grassroots idea, because a lot of people in management don't believe necessarily that their job is to be told what to do from the bottom, right?
Yeah.
So as relationships go, those ideas need to be managed so that the right people can own them.
You think the standard will make the case clearly enough for a non-programmer who's in management to understand it?
No, I don't. And frankly, I don't think a programmer coming out of school is going to be able to pick up the standard like any other standard. If you don't already have a pretty good base of knowledge, you can't apply standards. They're not recipe books, right? However, if you're pretty close and you have a good idea of what you're doing, you can learn a lot from reading the standards because there's an enormous amount of knowledge in there. But it's not. I've never seen an ISA standard that was paint by numbers, right? And if you remember when all of us were wrestling with S84, how it was like, well, how do you do these things, you know? And we had so many meetings with Paul Grun and you know, Angela Summers and
right.
folks that were in the room when these decisions were made in order to understand. It's really, really difficult to write things both you know, to be able to be prescriptive without writing something prescriptive. It needs to be performance based, and we need to back off from all the individual jargon of companies. Yeah. Anybody that pulls that off gets an award from me. I hope that answered the question.
Anything else?
None from here.
Okay. All right. Well, like I said, if you have a question, you know, submit it through Brent. I'm gonna take a minute just to kind of go back over events, just because I kind of rushed through them before. Like I said, I still need a speaker for the April meeting. So anybody who's interested in speaking, knows somebody who's speaking, or more importantly, interested in getting involved in the committee, we're kind of reforming those. We do that around this time every year, and we could use people to help, you know, kind of plan the programs and what we're going to do, and you know, and with marketing and all of that. The website, the local website is completely redone. It's isabatonrouge.org, and there you can get information on the events, subscribe to our newsletter. You can unsubscribe if you're not happy, but that way we can keep you in touch, and it's a new place to be at. So, also we had a request. Kenneth Hudnall with CDI is putting together a PE study group. So anybody who's interested in taking the PE exam, or honestly the CAP exam, a lot of the materials identical. I'll put that up on the website as well. You know, contact information so you can do that. I recommend it. I got my PE a while back in control systems, and one of the reasons I got it wasn't so much that I've ever used it. I've never pulled out the stamp. Right? It was, I looked at, well, this is all the information that they cover, and this is a lot of stuff that would be good for me to know. You know, a lot of instrumentation stuff about how a thermocouple works, and a lot of details that my degree's in mechanical. I never had any of that, so it was good. I think it's valuable, and I think the study group could be valuable. So if there's not any questions, you know, we'll probably go ahead and wrap up and let everybody go early. That was kind of one of the intent too in changing the format. Is I at most wanted the meeting to last an hour, but we wanted to kind of keep it a good tight meeting and let everybody get back to what they're doing. And I definitely appreciate any help. Jonathan or Brent, do you have anything before we leave?
I think we covered it.
Okay. All right. Well, I appreciate it. Now I'll let y'all get back on with your day. Again, please submit feedback. You know, either through the website or to me personally or whatever. Positive and negative. We want to know what worked. We definitely want to know what didn't work. And thank y'all for coming.
Thanks very much.
Right. The website is isabatonrouge.org. And ISA National is going to redesign their website soon. So they're coming up, I think 1st of April, they're going to kind of revamp things. So definitely in the interim, we're going to maintain our own site, and then we'll look down through the years as how things turn out. So, yeah, appreciate everybody for coming.